Geologic controls on northeast Wisconsin trout streams is Nelson Ham. Nelson is a professor of geology and environmental science at St. Norbert College in De Pere, Wisconsin. He is a geomorphologist and a glacial geologist with strong interest in the environmental history of Wisconsin trout streams. Nelson has worked for the Wisconsin Geological and Natural History Survey and the U.S. Forest Service in mapping projects in Lincoln and Oconto counties in northern Wisconsin. And in a past life, he spent 15 years as a fly fishing guide for a fly shop in De Pere, Wisconsin. So Nelson, we're looking forward to hearing about all this stuff. Right is forward.
Right is forward. Well, first I want to thank Ray for having me. I may seem like a little bit of an odd addition, but I hope what I'm going to talk about today, a little higher, works well when you're thinking about managing trout streams. Most of the talks I saw are about riparian management, forest management. Ellen's speaking a lot about the in-channel processes and processes close to the channel. And this is going to be a much different approach. It's a big picture approach to understanding the geologic conditions that kind of control where trout streams are in Wisconsin. I've been interested in this for a long time, and the reason is an old paper by people in the DNR who I assume Ray probably knew, Poff and Threinen. They were working in the Wisconsin Conservation Department, so the predecessor to the DNR in the late 1950s and 60s, and published a paper in 1963, which is actually after the paper where I got this quote, and it's on the geography of Wisconsin's trout streams. So it was essentially what they were doing is they were looking at the geologic controls on trout streams in the state. Well, we've had over 40 years of additional geologic work, so we know a lot more about specific locations, but the overall picture that they put together was actually really quite good, and it's a fun paper to read. What they did the year before that main paper came out is they published just a little 2-page article in the Wisconsin Conservation Bulletin, which are fun to go back and look at. They're all online. And they kind of summarized what they were working on for the big paper. And this is what they used as their opening quote. It says, geologic conditions for Wisconsin's trout streams were created when the glaciers melted. Our activities determine whether they remain trout streams or not. And I think that's particularly relevant to some of the conversations that we had on field trip the last couple of days and what I'm hearing today. This is actually the original map that they published in their 1963 paper. I know it's not entirely accurate any longer, but I just like using it. And where I'm going to concentrate is in the area that's in red. More broadly, it's the area that's in yellow. So the kinds of things I'm going to discuss, I think, apply to all of these or most of the trout streams that are in the northeast part of the state. But some of the specific examples and maps that I'm going to show you come from places that are around the reservation or in northern Oconto County, places that I had worked before. So to get started, what do I think of as being kind of the geologic requirements for having trout streams in this part of the state? And it's really not that complicated. But when you see a trout stream like this, which is the evergreen, I think that we'll see on the field trip tomorrow, you're looking at a relatively small area. And so you might think, well, the things that we need are good gravel for spawning. We need a high base flow, meaning the groundwater input, either from springs or seepage into the channel, is a really large part of the total flow of the trout stream. We have cover in terms of forest, and also in the case of streams that are on the reservation and elsewhere, lots of big boulders are available. But it's actually what's underneath the riverbanks on either side, back into the woods, that's the starting point of these trout streams. And that's going to be an abundance of sand and gravel that was originally deposited by glacial meltwater streams. And some of you may know the term outwash. We have a lot of outwash in the northeast part of Wisconsin that almost 1-for-1 matches up where most of the trout streams are. So why is that outwash so important? It's what gives the stream its gravel in the first place. But the second thing is groundwater can move through that gravel very readily. It has a very high hydraulic conductivity. And so in those geologic settings where you have the right conditions and you have the outwash, you're really maximizing the groundwater flow from the uplands into the valleys and into the stream channel. So this is kind of how I organized the talk. I want to review something that maybe not all of you are familiar with, and that's what's a braided stream and what's the outwash that I'm talking about. Kind of quickly go over the bedrock geology, a little bit about the glaciation of the state, which I know many of you are probably familiar with, and then just look at the broad picture of where the trout streams are and where they aren't. And we've got a little bit of time at the end. I want to show you some neat work that came out of the mapping we did many years ago and some recent work with me and a couple of undergraduate students, and that is records of fairly significant drought in this part of the state, many thousands of years ago. So what's a braided river? It's a river that we almost never see in Wisconsin and that most of you might not be familiar with personally. When Ellen was talking, she used multi-thread or single thread as terms to describe when you have a single channel river, where you have a river that has multiple channels that repeatedly disconnect and connect. That's exactly what a braided stream is. So the reason we don't see them in places like Wisconsin is they're really common at glacier margins. And the primary reason for that is, one, you have a large amount of meltwater available, although it fluctuates in flow between day and night and between seasons. Obviously, you get high meltwater in the summer, you get low meltwater in the winter. But even on a daily scale, when the sun comes up and the glacier is melting the most, you'll get maximum discharge late in the day into the evening. And then it'll start to slow down at night and you get low flows typically in mid-morning. So these are really variable hydraulic systems. The other thing is that the sand and gravel is the source of the braided stream deposit that's coming from the glacier. So the glacier is basically delivering lots and lots of sediment to the ice margin. The melting ice is what's providing the flow, and you get a system that I like to think of as being overwhelmed. And what happens in that particular case is the channels will break apart and then they'll reconnect. And the areas that are between them, which are these kind of lenticular or lens-shaped islands, we refer to as bars. Those bars are unstable. They don't have vegetation growing on them. They're very dynamic. They're easily erodible. And so what we have is a river system that's constantly changing, depositing in one place, eroding in another. So how do you recognize that you've got braided streams in a place like northern Wisconsin? Well, we use landscapes a lot, and especially the landforms that we could recognize originally from topographic maps, and then more recently, the digital elevation models that are created from LiDAR, which has really enhanced our ability to map things in more detail. I just wanted to show you a couple of pictures to have this in mind. Typically, when you see sand and gravel pits, almost anywhere in Wisconsin, but especially up here, they're mining outwash. They're mining the sand and gravel that was deposited by those meltwater rivers. And the thing that I want you to notice about this particular shot is almost everything is sand and gravel. Groundwater can move through that very easily. Infiltration from rainfall almost entirely goes into the ground. It's seldom the case that you get a lot of overland flow of water or stormwater runoff in these outwash terrains. This is going to be the lifeblood of the trout streams that we have in Northeast Wisconsin. Many places that are forested, even on the digital elevation models, you can't pick out oftentimes the individual braid channels. You can do that if the forest has been removed. And the slide that I put in here is a picture of the Eau Claire River, if I have this right, in west of Anago in Langlade County. And if you look and have the right time of year in terms of the photos, sometimes what will happen is you'll get enough of a contrast between soil moisture that you can pick out the old braid channels. And remember, I pointed out those kind of lens-shaped or lenticular bars. Here is a bar with two original channels that would have split around it. And then there's a number of other ones that you can pick out on there as well. Oops. So we'll come back to outwash. But I like that slide because it shows really the relationship I'm going to harp on, which is the trout streams almost one for one are developed in outwash deposits. But let me show you a little bit more about the landscape and the landforms. So there's a couple of things I want you to remember first about the bedrock geology. This is a really simple map of Wisconsin's bedrock geology. In general, if you're on the east, the south, or the west side of the central part, we have sedimentary rocks that are nearly flat line. And this cross section at the bottom is exaggerating that. The central upland, or the northern highlands, is where we have really complicated geology, very old rocks, and they're primarily igneous and metamorphic rocks in general. In the area of the reservation, we have one of the largest areas of one single lithology or rock type, and that's going to be the Wolf River Batholith. Every pink granite rock that you see on the field trip, or when you've been driving around this part of the state, all comes from that single unit. And it is located roughly in this kind of eastern part of that northern highland. The main thing I want you to recognize or remember from the bedrock map is how it controls topography. And it has a really important influence on the glacial landscape that developed here. Here's the reservation. Here's northern Oconto, and the Trout Stream region we're talking about is primarily up here. The regional slope of all of this landscape is towards the Green Bay lowland, right? And the drainage is part of the Great Lakes drainage. The moraine, the terminal moraine of the what's called the Green Bay lobe, and I'll show you a map of that in a second, is right here. It separates the flow then on the other side that goes to the Mississippi drainage, right down the Wisconsin River Valley. But this regional slope, it's over 1,000 feet from here down to Green Bay, really had a strong influence on the style of glaciation that took place. So now we're going to move on to the glacial geology. The area that we're looking at is primarily up here. This is a simplified map of the areas that were covered by the ice sheet during the Wisconsin glaciation, which is the last one. And the only thing I want you to concentrate on is the areas that are in white. That was the shape of the ice margin. It was distinctly lobate, we like to say, which means it's not one kind of gentle, very straight ice margin. It has these various tongues to it. The main cause of that was the fact that the ice was moving through the Great Lakes lowlands. It was coming through Green Bay, down the Lake Michigan basin, and through Lake Superior into northern Wisconsin. And it was getting thin, going to zero at the ice margin. The thinner the ice is, the more it's controlled by topography as it moves across a landscape. And so as a result, we got this lobate margin. And we name each part based on geographic features. The area that we're in is an area that was glaciated by the Green Bay lobe, and the arrow shows you the ice flow direction. It was not to the south here. It was almost due west and a little bit north of west. Another thing you'll see in the DEMs that I have is that I also include part of this lobe, which is the Langlade lobe. The Langlade lobe was coming over the UP right about here and then going straight to the southwest. And they joined at a really prominent junction in the landscape called the Anago Flats. And I know most of you have probably driven that as you go towards Anago. The break from the area that was covered by ice to the area beyond it is really obvious on 64 when you're going to Anago, because you leave the forested landscape into the cleared landscape, which is essentially all outwash that was draining off of the ice margin. So that little red circle I put on there just for reference. And so on a couple of the other maps, you'll kind of know where you are, even though there aren't a lot of place names on those. So how does this look like to a glacial geologist looking at landforms? And I'll show you some closer pictures of this in a little bit. This is a digital elevation model that's generated from 10-meter DEMs, although now we can do it also from LiDAR that has a spacing of 1 meter. The area that is the junction between the Langlade lobe and the Green Bay lobe, the Anago Flats, is this really prominent large flat area there. The terminal moraine of the Langlade lobe was here. The terminal moraine of the Green Bay lobe was there. The different colors obviously indicate and stress elevation. Highest elevations are here, well over 1,000 feet, over 1,500 in some places. And then you go back to the Green Bay lowland. But the thing to know about this landscape when you first look like that, it's a composite. And that's often makes it difficult to interpret at first. So what you have is the landforms that were made when the glacier advanced, and superimposed on top of those, draped on those, are the landforms that were made in the deposits when the glacier retreated. So we're going to look at, what are the advanced landforms versus the retreat landforms? And the retreat landforms are the ones that are really important for making trout streams. This is an old kind of cartoonish picture that was published in a paper by some geologists, now retired, that spent a lot of years kind of forming the foundation that we know of understanding the glacial geology of the state. And it basically was, what's the sequence of landforms that developed close to the ice margin when the glacier was at its maximum extent? So it's covering the entire area. And from a time perspective, this would be somewhere between 20 and 30,000 years ago for most of the state. So think of most of the state being under ice for at least that interval of almost 10,000 years, which is a lot longer than we thought in the past. So here's what the glacier system looked like when the ice was at its maximum. It's building a terminal moraine here, and underneath it, as it's sliding, it's forming drumlins, which are the streamlined hills, right, that indicate ice flow. So it's molding the landscape underneath it. But when the glacier finally retreats, oftentimes the terminal moraine zone is very hummocky. It's got a very hilly topography to it. The reason for that, and we see that consistently in the northern part of the state, is what's not shown on here is that the ice in the marginal zone became very dirty. So it had lots of sand, silt, and clay and gravel that was frozen into it. That material also melted out on top of the ice. When all of the ice finally disappears, it's laid down in this sort of haphazard pattern in the landscape, lots of kettle ponds and lakes, typically really poorly organized stream systems and drainage. And that becomes this hummocky landscape that kind of parallels the ice margin and really forms the major moraines that we see. And again, I'll show you some pictures of that. Then also here are the drumlin forms, which are elongated parallel to the direction of glacier flow. Here's what that landscape looks like when it's really obvious. And this particular DEM follows State Highway 29 from Shawano, and just off the slide over here would be Stevens Point. These kind of elongate hills, of which there are a few hundred probably that we could pick out on here, that are oriented roughly northwest to southeast, are the drumlins. You'll see that there's a pretty prominent ridge here and here. Those are two of the major moraines that formed when the ice was close to or at its maximum. And those are the primary landforms that I just showed you in that diagram. So these are hummocky. They've got some relief to them. The drumlins formed underneath the ice, but there's clearly lots of other deposits that are in between those drumlins. Those are the things that formed as the ice was actively retreating. And so I want to show you a little bit about that. This was an old diagram that a colleague of mine, who's really my mentor at the State Geological Survey, John Addig, and I put together when we mapped northern Oconto County for the U.S. Forest Service. And we were trying to figure out, can we make sense of this landscape and give people an idea of how it developed over time if things were a little more idealistic than we see today. And the model that we put together based on the geologic mapping is that the ice sheet, basically as it was retreating back into the basin, so that's why we draw the bedrock topography essentially going right back to the right. This would be to the west, and over here would be to the east, is that periodically the ice would stall. It would shed tremendous amounts of sand and gravel and braided outwash streams off the front of it. And instead of forming a classic moraine, we formed something that's the braided river equivalent of a moraine, which is what we called an outwash head or a head of outwash. And much of the landscape in this northeast part is primarily these outwash heads. So what would happen is if the ice stalled here, it would build one of these outwash heads. So essentially what it is it's a coalescing of braided outwash fans that generate a really long structure. And I'll show you some map views of that in a second. Sometimes the ice would break off and be separated in chunks and get buried partially or entirely. The ice sheet would retreat to another position, form another outwash head, another position, form another outwash head, and then it retreated back into the basin. My blue arrows and areas on here are primarily where the meltwater streams were flowing. When the outwash head is right there, you have braided streams that are flowing continuously across that surface, and they're flowing primarily away from the ice margin because it's built up this ramp that's sloping in the direction that the ice originally was flowing. That continues here. But what happens is, as the ice is retreating back, if you can imagine that out of the board is to the south and in is to the north, it's an uneven ice margin. The meltwater that's coming off of those outwash heads starts to turn and flow to the south because it can't go to the east because the glacier's sitting in its way. And so we had a lot of parallel ice marginal channels. They were ice parallel. They were running right along the ice front. So when I show this little meltwater stream here, imagine that water is coming out of the board at us, which would have been to the south. Sometimes the water would pond if there was a deeper basin in front of the ice and form a glacial lake. And there's a very large one that we recognize in eastern Wisconsin called Glacial Lake Oshkosh. That was just one different kind of meltwater style versus the braided outwash streams that I mentioned earlier. For the most part, the trout streams that we see in northeast Wisconsin have reoccupied some of these meltwater channels. For obvious reasons, those are the lowest places in the landscape. That's where the water is naturally going to flow. So what I like to think happened in the landscape over time is outwash heads first, big meltwater channels, and then as the glacier is leaving, the meltwater is going down and we have simply groundwater or rainwater driven flow. You get the trout streams that basically sit themselves down in those old meltwater channels. It's not universally true. There are places where basically that meltwater starts to flow, and I mean the modern water flow, the modern discharge starts to turn and find places to cut across the landscape and flow to the east. And you'll see that in general, the pattern of meltwater streams that we see here is some segments are basically northwest to southwest segments, and all of a sudden there'll be a 90-degree angle turn or bend in the river system. That's where the water is still being funneled into one of these meltwater channels that was flowing right along the ice margin. Oops. Let me show you real quickly what one of these really great outwash heads look like when it's almost perfect in my mind. This is a slide of the DEM for an outwash head that's north, just a few miles north of White Potato Lake in the eastern part of Oconto County. Here is the topographic profile taken from a point about here to back here. And hopefully you can see that it definitely has a slope, that would have been away from the ice margin. This entire surface here that's relatively flat is nothing but outwash. Those would have been braided stream fans that were coalescing off the ice margin. And the ice margin would have been right here. So when this outwash head was forming, this low area was entirely filled with ice. There's an old abandoned meltwater channel that's cutting through that surface. There's no stream in it now. The water table is too low. Oftentimes those channels formed on the outwash heads in places where the ice backed away a little bit and formed a lake. So you had a particular outlet that opened up, formed a channel in the outwash head. And once the ice backed away from this ice contact face, everything drained. The thing that I'm not pointing out, and I'll come to a little bit later, is this doesn't look like it's in place, right? This outwash meltwater channel all of a sudden disappears right here and you can't find it morphologically over there. These are younger sand dunes, inland sand dunes that postdate glaciation by a couple thousand years. And I think they're relevant and important to thinking about long-term changes in climate and impact on the water table, trout streams in this part of the state. We have time at the end. I'll show you a little bit about that. So this is the old glacial geology map from Wisconsin, made in the 1970s. But sometimes the old maps are more helpful than some of the newer ones because they were a little bit more simplistic. And the main thing I want to emphasize is how much of the landscape is underlain by outwash in the Northeast. Here is the junction between the Langlade lobe, which was flowing this way, and the Greenlade lobe flowing that way. Anything that's brown on this map are either moraines or drumlins. So all of these light brown areas that look like islands or patches in the landscape are the drumlinized uplands. The long, relatively dark, kind of narrow ribbons represent moraines, and all of the orange or yellow on that map represents outwash. Percentage-wise, in the northeast part of the state, we have far more outwash in the landscape than we do moraines and drumlins, which are typically composed of a different kind of sediment, much lower hydraulic conductivity that we call till. And then the other thing is you'll notice that here's Shawano Lake in dark blue. The light blue represents places that were glacial lakes. And this particular basin here, which extends down well into the Fox Valley around Lake Winnebago, is Glacial Lake Oshkosh. This is part of it as well, but as the ice was backing away, you actually had multiple different lake levels. And remember I said that lakes sometimes formed in places where the water was ponded because it couldn't flow to the east. It didn't have an outlet. And that's exactly what happened when the glacier sat right here along this moraine, is you had the right local conditions in order to pond meltwater instead of having it run off as a braided river. Okay, to kind of summarize, if you go back, here's the DEM now just of northern Oconto County. It looks pretty complicated. There's a lake basin down here. That's Glacial Lake Oshkosh, the northern part of it. The outwash head I showed you is just off the map. Most of this surface consists of fairly flat surfaces. Does that stand out? So we get big patches of relatively flat uplands, and then they're kind of dissected by lower places. The higher surfaces represent all of those former outwash heads. And then where you see kind of the dissected surfaces, there's a topographic grain that's primarily northeast to southwest. Those are the meltwater channels that formed as the water basically started to confine itself at lower elevations and erode through those old outwash heads. So where are the trout streams in northeast Wisconsin? And hopefully I'll make the case with one last map. They're in places where we have abundant outwash. The outwash maintains really good groundwater connection to the stream channel. It maintains the base flow as being fairly high. It provides the sand and gravel for the stream bed, for good hyporheic exchange, which we've talked about a little bit in some of the other talks, and also for spawning gravel. In addition, the stream flow directions, the ones that we see in this northeast part where I mentioned stream segments going to the southeast and then all of a sudden taking a 90-degree bend and then going back to the southeast again, those stream patterns, those drainage patterns are being controlled primarily by that landscape of outwash heads and then the late stage meltwater channels. Where we don't find trout streams in northeast Wisconsin is almost anywhere there are clay tills, meaning we have really low hydraulic conductivity in terms of the glacial deposits, and even on some clay to even sandy lake plains when the relief is exceptionally low. And the streams would have a very, very low flow gradient. Just two quick examples that I hope most of you are familiar with. Elton Creek, which is a small trout stream that flows in here, is flowing in an old meltwater channel. It did not erode that large, relatively deep channel, but it's obviously following it now. Some of these other less continuous low areas represent places where there were ice blocks in some cases. When they're entirely connected and through flowing and have streams in them, they were meltwater channels that formed as the outwash heads were being abandoned. Another one that I like that'll just show you an example of a stream segment that was parallel to the ice margin and it still controls the flow today. This is in northern Oconto County. Here's McCaslin Brook, which is a tributary of the north branch of the Oconto. This large kind of almost cataract-like valley is much bigger than the stream that's in it today would create. That's also an old abandoned meltwater channel. And McCaslin has simply found a place in the landscape to kind of cross through one of these big outwash heads and connect up with the north branch, which flows to the south. So in simple, this is my GIS, very simple GIS, because I like using this old glacial map. This is the glacial map of Wisconsin now. The thing to remember is the orange is outwash. The yellow is also outwash. Here's Glacial Lake Oshkosh. Anything that's brown on this slide represents areas of tills that typically have much lower hydraulic conductivity. The district of trout streams that I consider kind of the northeast, and I even included those that go a little bit further south, are almost 1-for-1 in the sandy outwash sediment that was deposited either by the Langlade lobe or the Green Bay lobe. Remember that we have the Lake District up here. The reason that they're in this area is because the regional slope started to tell them to go that way. And they end really abruptly. You've probably noticed this on the map before of trout streams. There's a very sharp line that defines where the end of trout stream water is located. Almost one for one, that boundary matches up with the transition from braided stream outwash to clay tills or the low relief plain of glacial Lake Oshkosh. Lastly, where aren't they? Even though I just mentioned that, Ray, when he started talking at first, had a nice base flow map right of Wisconsin. And if you remember it, there were two kind of large holes in the state where base flow index is fairly low. They correspond to the central part of Wisconsin, which has some older clay or tills as well. And then the other section of it is right almost one for one with that area of clay tills and also the glacial Lake Oshkosh basin. How am I doing on time? Just a couple of things left. Where did those clay tills come from? And this is just a different way of looking at the distribution of the trout streams. One of the things that we realized from work years ago in the eastern part of Wisconsin is that there's two very different areas of tills. What's called the Holy Hill Formation is the deposits that basically were associated with the early advance of the Green Bay lobe when it first came into the state. But then there's a very distinct change to a reddish brown clay till and also reddish brown clay lake sediment in the glacial Lake Oshkosh basin that we call the Kewanee Formation. One of the major changes that happened to cause that difference is when the ice was at its maximum in the eastern part of the state 20 to 30,000 years ago, as it was retreating back into the basin, it actually retreated out of the Green Bay lowland entirely up into the UP. And there was drainage of reddish brown clay sediment from the Lake Superior Basin into Green Bay. The ice one last time re-advanced over it, smeared that clay sediment out over the landscape. And today the boundary between trout streams, which I showed you in the geologic map earlier, is also the same, almost one for one, as this boundary between the Kewanee and the Holy Hill Formation. Do I have a couple minutes left, Ray? Okay. I wasn't sure if we'd have time for this, but I wanted to mention the sand dunes. When we mapped for Northern Oconto County, and that was funded by the U.S. Forest Service 30 years ago, we only had topographic maps to work from for interpreting the landscape. But one thing we noticed is that, especially on the northernmost part of glacial Lake Oshkosh, there were really extensive sand dunes that developed. But they're stable now. We first thought that they blew up as the lake first drained and then became stable. But a new dating technique to date the time of movement and burial of the sand called Osl Dating, it's optically stimulated luminescence, told us that these dunes post-date glaciation by at least 2,000 years, and in some cases 3,000 years. So at least for some time, well after glaciation was done, there probably was a very large regional drought that extended over northern Wisconsin well into the UP, because we find similar dunes of similar ages throughout northern Wisconsin, parts of even Minnesota, throughout the upper peninsula of Michigan, even in central Wisconsin over the old glacial Lake Wisconsin lake plain where the central sands are, and again distributed in other places around the state. The implication for that is a really big drop in the water table over a large area of the landscape. And so one interesting thing I think when you're thinking about trout streams is that they didn't just form at the end of the last ice age and they've been there forever. They may in many places completely disappeared in terms of flow if the water table decline was too great, become warmer because the base flow index became lower over time, and then reestablished themselves and probably expanded again once this interval of relatively dry conditions, these drought conditions, were over probably around 8,500 to 9,000 years ago. Okay, so the sediment that's on the lake plain in this northern part was primarily sand. It was a sand bed lake. Again, because we were eroding lots of sand and gravel from the outwash that's around it. What happens is that surface, as it got drier and drier, once the sand was exposed again, the wind starts to blow. Dunes are geomorphic features that are active. They change position over time. They always move in the direction in which the wind is blowing. And many of these are a type of dune that we call parabolic because it has this kind of parabola shape. You can't see it quite as well in some of these ridges because they've run into each other over time. But the slip face, the steep side of the dune, which in this DEM is always in shadow, always faces in the direction in which the wind was going. So the dominant winds were coming from the northwest and going to the southeast. Is this the end of any kind of drought interval in this part of Wisconsin? And I'm going to leave you with one last photograph. Frederick Thwaites was a really amazing glacial geologist who did some of the first glacial maps of northeast Wisconsin, primarily working up here in the 1930s and 40s. And he was always very meticulous in terms of taking photographs and documenting them for the State Geological Survey. It's a large archive there. This is a picture of a dune that we're pretty sure was taken right about 1930, could have been 31 or 32 when he was here. In the northern part of Oconto, sorry, the southern central part of Oconto County, on part of the sandy portion of Glacial Lake Oshkosh, that reactivated during the Dust Bowl. Did the entire dunes reactivate? No, there's no evidence for that. But the upper few feet of those inland dunes that formed several thousand years earlier pretty consistently show that they reactivated, probably for just a few years to a couple tens of years, because Dust Bowl conditions extended, believe it or not, well into this part of Wisconsin. It's well documented for the central sands, where we had dunes also reactivating, but it also impacted the northeast part of the state, again, where our trout stream region is. I think that's my last slide. I'll stop there and take questions if there's a little time for that. Quick question? Sure.
Was it mainly the logging that had taken place in the fires or agriculture?
The early stage, of course, couldn't have been either one. Sorry. So you asked what was the product of basically the reactivation of the dunes?
What was the reason? What
Right.
opened the land up, allowed the dunes to form?
For the Dust Bowl era,
The Dust
the
Bowl.
late Bowl era, we almost see that entirely in agricultural areas. It's not a large part of the landscape. Some of you may know that the state UW-Madison, the geography department years ago, put all of the earliest aerial photos for the state online, so you can look at them from the 1930s. When we've looked at those and found these places where the dunes reactivated, they were all on agricultural fields. But in terms of a percent of the dune landscape that reactivated, that doesn't look that much. 5 to maybe 10% at most, but all of the reactivation is primarily in areas where agriculture had taken place.
Thank you.
Yep.
Very, very interesting. Other questions? Okay, that helps us stay on time here or get back on time a little bit.